This is lesson 1.1, unit 1, lesson 1, using tree diagrams to calculate probabilities. So in this lesson, I'll teach you guys what a tree diagram is, but before we get into that, we're going to review some prior knowledge here. We're going to review what is probability in math. So hopefully you guys already know a little bit about probability, maybe you remember, but we'll start with the definition here. When we talk about probability in math, we are talking about the likelihood that an event occurs. So we're going to go ahead and put that in our notes here. The likelihood that an event occurs. And when I say event, I'm just talking about anything that can happen. So probability is just a measure of how likely is something going to happen. And if you guys remember from when you first learned about probability, we usually write probability as either a percent, so 20%, 50% chance, 100% chance, or a decimal. And of course, you guys should know that decimals and percents are basically the same thing. For example, 100%, that is, this event is definitely going to happen. There is a 100% chance of happening. As a decimal, we would write that as 1.0. Okay, now to calculate probability, we say that the probability of event A, so some random event happening, we'll call it event A, well, that's going to be equal to the number of times A occurs and we're going to divide that by the total number of outcomes. So the number of times A occurs divided by the total number of outcomes, or total number of events. Okay, it's a fraction. It's a ratio, guys. So let's look at these two examples, and I can show you what I'm talking about. So when we look at the examples below, we've got two really common, really easy examples to calculate the probability for. So the first one says, what is the probability of getting a heads whenever you flip a coin? So you guys should know, if you're flipping a coin, you really only have two outcomes, either heads or tails. And so if I'm calculating just the probability of getting heads, if I use my little formula, I could say the probability of getting heads is going to be equal to the number of times that the event heads occurs. So I flipped the coin once, I got heads. That means I got heads one time, divided by the total number of possible outcomes. So, like I said, when you flip a coin, you really only have two outcomes. You can either get heads or tails. So we would say this probability is equal to 1 over 2. And of course, if you put that in a calculator, you'll get 0.5, which we all know that is a 50% chance. There's a 50% chance of getting heads when you flip a coin. Okay, another really common, really simple example is, what is the probability of rolling a 6 when you roll a die? So very similar, I can use my formula here. And I could say the probability of getting a 6 is equal to the number of times I got a 6. So I rolled it once, I got a 6 one time, divided by the total number of outcomes. Well, you guys know when you roll a die, you can either get a 1, 2, 3, 4, 5, or a 6. So there are 6 possible outcomes. And if I plug this into a calculator, I'm going to use a little squiggly equal sign here. Here, I can draw that better. Looks like this. A little squiggly equal sign, that means approximately, because this is going to be a nasty decimal. It is 0.166, and that 6 repeats over and over and over. So 0.166666666. And if we round a little bit, we can say this is about a 16.7% chance. So when you roll a die, you have a 16.7% chance of rolling a 6. Okay, so that's a little quick review on probability. Let's talk about what are tree diagrams. So if we go down here to the bottom of the front page of our notes, I have a definition for you. It says tree diagrams are a useful tool to help us visualize probabilities of mutually exclusive events. And I bet that this term right here is probably a new one for most of you. So right after that, that next sentence, that is the definition of mutually exclusive events. We would say that mutually exclusive events are events that cannot occur at the same time. So if you have a highlighter on you, I would highly recommend getting that out and highlighting that sentence in your notes. And I'll talk for just briefly about what that means. So events that cannot occur at the same time, things that are mutually exclusive. If you go back to that flipping a coin example, if I were to flip a coin, let's say 4 times, well, we know that each time I'm either going to get a head or a tail, right? I can't get heads and tails at the exact same time. That's because I can't flip the coin more than once all at the same time. It would be really weird to flip one coin 4 times all at once. That's impossible. If you had 4 coins, you could do it, but you cannot do that with one coin. We would say that each coin flip is a mutually exclusive event. Just because you got heads once doesn't mean you're going to get it the next time. That's what that means. And if you look at these examples we have in the box below, you see that we're also talking about die again, so rolling dice. Same deal. You can't roll a die and get a 1 and a 6 at the exact same time. You would either have to roll it twice or you'd have to roll 2 die. They are mutually exclusive events. Okay? So, let's talk about tree diagrams. Now, tree diagrams are just pictures that we draw to help us visualize these probabilities. So, in the top left box here, we're going to draw what a tree diagram would look like for a fair coin. And we'll come back to that word fair in just a moment. Okay? So, for a fair coin, all right, what I'm going to do is I'm going to start my tree diagram, and it's exactly like it sounds. It looks like a bunch of branches. I'm going to draw however many branches I need for every possible outcome. So for a coin, right, we've already talked about this. You either have heads or you have tails. So we're going to draw one branch coming out one way and one branch coming out another way because there are only 2 possible outcomes. I could either get a heads or I could get a tails. And that's it. That's all you have to do for a tree diagram. Now, what we also normally do is we go ahead and label the branches of our tree diagram with the probability of that event occurring. So we already talked about it in one of the previous examples. The probability of flipping a heads is 50% or 0.5. So I'm going to go ahead and label that branch 0.5. And then, of course, we know tails should be the same probability. I have a 50-50 shot of getting heads or tails. So on that tails branch, there's also a 0.5 probability. Okay, very good. Now, if we look at the tree diagram for a fair die, so in the top right box over here. Now, this one is going to have a little bit more branches, right? Because a die has 6 possible outcomes. So it's going to look very similar, except I'm going to break this off into, oops, let me use my nice straight line tool here. I'm going to break this off into 6 different branches, just like that. Okay, and then of course, you're going to go ahead and label all the possible outcomes. So you could get a 1, you could get a 2, a 3, a 4, a 5, or a 6. Just like that. So a little bit more branches, kind of a crazier picture, but it's still just a tree diagram for this situation. And of course, we can go ahead and label our probabilities again. For a fair die, we have a 1 out of 6 chance of getting each of these. So I can label each branch 1 out of 6. Just like that. This is what a fair die would look like. Now, if you'd like to, take a moment, maybe pause the video, think about it. In the bottom two boxes, we're going to try and draw examples of tree diagrams for an unfair coin and an unfair die. So I want you guys to think about for just a second, what do you think that would look like? Okay, so talking about the coin first. If you guessed that maybe the tree diagram looks exactly the same, it's got two outcomes, but the probabilities are not the same, then you were right. You guessed correctly. In an unfair situation, okay, this would mean you still can only get heads or tails, but this would mean one of them, let's say heads, has a greater chance than the other. So let's say I have a 75% chance of getting heads and a 25% chance of getting tails. This would be considered unfair because those probabilities are not equal. You would expect when you flip this coin that you're probably going to get heads more often than you're going to get tails. Okay, so real quick, what we can do is we can go ahead and highlight fair and unfair, and we can maybe jot ourselves a quick note off to the side. Fair means equal probabilities. So every event has the exact same probability. And we can say unfair is an unequal probability. Okay, all the events are not the same. Okay, very good. So once again, maybe pause the video real quick, see if you can draw a tree diagram for an unfair die. I'm going to draw one in 3, 2, 1. Okay, so same deal. We have 6 possible outcomes. 1, 2, 3, 4, 5, 6, something like that. Oops, that last line was really bad. Let me fix that. Let's put it up here instead. There we go. Okay, so again, I could get a 1, I could get a 2, a 3, a 4, a 5, or a 6, right? Okay, but in an unfair die, remember these are uneven probabilities. They're not all the same. Some of them might be the same, but they're not all equal. So let's say, I don't know, for 1, I have a 1 out of 20 chance. For 2, let's say I have a 3 out of 20 chance. For 3, how about a 4 out of 20? 4, I could put something like 10 out of 20. 5, I could put 1 out of 20. 6, I could put 1 out of 20. And once again, this is just an example, right? You could have put something totally different than what I put, and that's fine. But what I want you to pay very close attention to is I am not just pulling these numbers out of thin air. Okay, there's a lot of, you might be thinking, well, where do you get the out of 20 thing? The 20 part doesn't matter. What matters is they all have to add up to 100%. So this might have seemed like I was pulling these out of thin air, but if you double check, 1 out of 20 plus 3 out of 20 plus 4 out of 20 plus 10 out of 20 plus another 1 out of 20 plus one last 1 out of 20. If you add all that up, you'll get 20 out of 20, which is 1. That's 100%. And if you double check all of these real quick, you'll see that they all do that. For a fair coin, 0.5 plus 0.5, that's 1, 100%. For an unfair coin, 0.75 plus 0.25, that's 1, 100%. Same thing for our fair die. If I have 6 of these 1/6, well, 6/6 is 1. That's 100%. So what that tells us is tree diagrams are useful because they help us visualize probabilities. They also help us double check and make sure we're doing our math right. All of the probabilities in a tree diagram should add up to 1. If not, that means you probably missed an event or a branch. Something is not quite right. So that's just a real quick, good way to double check that you're doing some of these probability problems correctly. Okay, so speaking of, let's try a couple problems here. There's one other thing I want to show you about tree diagrams. Tree diagrams don't have to split off once. They can split off as many times as they need to. They're really good at helping us visualize multiple events happening over and over and over. So for example, what do I mean by that? It says tree diagrams can also be used to help predict probabilities of multiple events occurring, more like back to back. So instead of just flipping the coin once, this says what is the probability of getting two heads in a row when you flip a fair coin? Well, that means I had my tree diagram, right? I flipped my coin and I either got heads or I got tails. We know that already. But if I'm going to get two heads, that means I must have flipped my coin again. And so this is actually going to break off into even more branches like this. So after you flip it once, well, you're going to flip it again. You have two outcomes when you flip it again. So you could have gotten heads again. You could have gotten heads, then tails. You could have gotten tails and then heads. Or you could have gotten two tails, just like that. And again, this word fair, right? That means for every single one of these splits in the branches, we have an equal probability. I have a 0.5 probability of getting a head and a 0.5 probability of getting tails. And that's the same over here too. So my tree diagram is going to look like this. And what it asks me is, what is the probability of getting two heads in a row when you flip a fair coin? Well, this is why tree diagrams are really useful. If I start at the beginning and I just follow my branch to the first heads, and then I follow it again to the second heads, this chain of events right here is going to help me calculate my probability. The first heads had a 0.5 chance. And then the second heads had another 0.5 chance. So I had a 50% chance of getting heads the first time, and then I had 50% chance of getting heads the second time. In other words, I need to figure out what is 50% of 50%. That's going to tell me what the likelihood is of getting heads twice. All right. Now, if you caught what I just said, maybe you had a math teacher that was really, really good way back in the day that taught you what the word of means in math. When I say 50% of 50%, that means I'm multiplying those two together. So, in other words, I could say the probability of getting two heads is equal to 0.5 the first time times another 0.5 for the second time. And if you guys put that in a calculator, 0.5 times 0.5, that is 0.25. Oops. Let me fix that real quick. 0.25. Or we know that's 25%. So there is a 25% chance of flipping a coin and getting two heads in a row. Now, one other quick thing I want to show you, this is why tree diagrams are really useful. Let's say you forget that you need to multiply those two together. Well, 25%, if I were to think of what would that be as a fraction? 25%, 25 cents, a quarter. 25 or 0.25, that is 1/4, right? And so if we go back to our probability formula, you have the number of times an event occurs divided by the total number of outcomes. Well, if you look right here, guys, when you flip a coin two times, you have four possible branches that you could end up on. Right here, we have this branch, we have this branch, we have this one, and we have this one. And only one of those is highlighted. So in other words, I have a 1 out of 4, or a 25% chance that I flip two heads in a row. Okay, so hopefully this is making sense. Like I said, tree diagrams are just very useful pictures that help us solve these kinds of problems. Okay, so let's look at a few more examples. I think we have 3 more to go. So it says, example 1, use a tree diagram to determine the probability of rolling a die twice and getting first a 1 and then a 5. So this is going to be very similar to the last problem, except now we're talking about dice instead of coins, right? Okay, so we rolled a die once. That means we have 6 branches coming off here. Something like that, right? Okay, now this is going to get really crazy because you could sit here and after each one of these branches, each one of these needs to also split off 6 times, okay? But because that's going to be crazy to draw, I'm only going to do it once, all right? So this is, I got a 1, this is a 2, I rolled the die and got a 3, a 4, a 5, or a 6, right? Okay, this says rolling a die twice, first getting a 1, and then a 5. So first I got a 1, and then off of this branch, I have 6 more possibilities. Oh gosh, it's really bad. Okay, so I have 6 more possibilities. Something like that, right? So please feel free to make your picture far prettier than I'm making mine. But I'm just trying to show you guys that these tree diagrams are useful, but they can get really crazy really quick, okay? If you think about it, if each of these have 6 branches coming off of them, you have 6 branches here, then 6 here, 6 here, 6 here, 6 here. You have 6 times 6 branches. So there's 36 possible ways that this could shake out, right? Okay, great. So we're going to hold on to that. Hold on to that number 36 in just a moment. Okay, I know that to get a 1 that first time, I had a 1 out of 6 chance of getting that 1. And then it says I got a 5 the second time. So if I follow this branch to the 5, well, I know that second time I also had a 1 out of 6 chance. Okay, so once more, if we follow that branch, first I had a 1/6 chance, then I had another 1/6 chance. I could say the probability of getting a 1 and then a 5 is equal to 1 over 6 times 1 over 6. Okay, and if you guys remember multiplying fractions, you just multiply straight across the top, straight across the bottom. So this is 1 over 36. This is the probability of getting a 1, then a 5. Okay, you guys remember just a minute ago we mentioned that if we were to draw all of these branches, there would be 36 branches. That's because there are 36 possible outcomes, and we only had one of them that we were interested in. There is a 1 out of 36 chance of rolling a 1 and then a 5. Okay, let's look at another one. A very similar one to the one we just looked at, where we have branches breaking off of branches. Okay, this one says you are off to a soccer game and you love being the goalie, but that depends on who is coaching today. With Coach Walls, your chances of being goalie is 0.5, or 50% of the time. With Coach Pablo, your chance is zero point 0.3, or 30% of the time. Coach Walls coaches games more often than Coach Pablo does, about 6 out of every 10 games. What is the probability that you will be a goalie today? Okay, so the first thing I notice, real quick, right off the bat, I'm going to determine how many probabilities was I even given here, okay? So the first thing I notice is the probability of Coach Walls putting you in for goalie, that is 0.5. So right there, okay? I'm going to switch colors here. The probability of being put in for goalie for Coach Pablo is 0.3. Great. And then maybe pause the video, think about it for a sec. There's actually a third probability you're given here. I'm going to show you in 3, 2, 1. Okay, so it says that Coach Walls coaches games more often than Coach Pablo does, and it says he coaches about 6 out of every 10 games. Well, if we think of this as 6 out of 10, it's a fraction. It looks just like our probability formula. That means that this probability right here, Coach Walls coaches 6 out of every 10 games. That's our third probability that we were given. Okay, very good. All right, now let's see if we can draw a tree diagram for this model. So the tree diagram is what is the probability that you will be a goalie today. So we're going to draw this tree diagram from your perspective. So you show up to the game, and before you even figure out if you're getting put in or not, you probably need to know who's coaching the game, right? So you show up to the game, and there are two possible outcomes. Either Coach Walls is coaching or Coach Pablo is coaching, right? Okay, so I'm going to put W for Walls, and I'm going to put P for Pablo here. Okay, cool. And we know that Coach Walls coaches games 6 out of every 10 times. So the W branch is going to say 6 out of 10. In other words, that is 0.6. Okay, now remember, all of the branches for every level of a tree diagram need to add up to 1. So if Coach Walls coaches 6 out of every 10 games, that means Coach Pablo must coach the other 4. So that means Coach Pablo, it's a 4 out of 10 chance, or 0.4. All right, very good. Now we got to break up our tree diagram even more. So if Coach Walls is the one coaching, it says your chances of being goalie is 0.5. So here, we're going to break this off into two possible categories here. And we're going to say, I'm either a goalie, G, or I'm not a goalie, in G. So goalie, no goalie. And we know that there is a 0.5 chance of me being a goalie, which means there must also be a 0.5 chance of me not being goalie. Very good. Okay, finally, same deal for Coach Pablo. I'm going to say, okay, he's either going to put me in at goalie or he's not. So goalie, no goalie. Okay. And I can say there is a 0.3 chance of being goalie with Coach Pablo, which means there must be a 0.7 chance of not being goalie. Okay, it says, what is the probability that you will be goalie today? So we need to follow all of the branches that result in us ending up a goalie. Great. So I know right here, here's one. So that means I need to follow this branch. Coach Walls was coach and he put me in. And that means here's the other one right here. The other possibility is Coach Pablo was the coach and he put me in. Okay, now this is a really interesting problem because there's actually two different chances that I might end up goalie. And so what I'm probably thinking I should do is figure out what is the probability of this chance, what is the probability of this chance, and then I should add them together. Okay, simple enough. So right here, for this one, I can say the probability of being goalie with Coach Walls is equal to 0.6 times 0.5. Okay, if you put that in a calculator, you will get 0.3. In other words, there is a 30% chance of being goalie if Coach Walls is coaching. All right, cool. Well, here's the other probability, this branch right here. So I could say the probability of being goalie with Coach Pablo is equal to 0.4 times 0.3. Okay, and if you put that in a calculator, you're going to get 0.12. or a 12% chance. Okay? So in one outcome, I have a 30% chance. In another outcome, I have a 12% chance. However, either outcome, I still end up goalie. So overall, so the total probability of being goalie is going to equal that 0.3 from Coach Walls plus that 0.12 from Coach Pablo. All right. So that means I have a 0.42 or a 42% chance of being goalie at the game today. Okay, so less than 50% chance. It's probably not that likely that you're going to be goalie. I don't know. Maybe you're not that good. Whatever. But you have a 42% chance of being goalie today. Okay, let's look at one final problem, all right? We can do lots of cool things with tree diagrams, and this one is an example of that. Okay, so this one says a travel agent plans trips for tourists from Chicago to Miami. He gives them 3 ways to get from one city to the next. So from Chicago to Miami, we can either take the plane, the bus, or the train. Then it says once the tourists arrive, there are 2 ways to get to the hotel. Either take the hotel van or taxi. The cost of each type of transportation is given in the table below. And it says, what is the probability that a person's trip to Miami from Chicago costs more than $300? Okay, cool. So let's make our tree diagram for this situation. So once again, we're the probability that a person's trip. So we're doing this tree diagram from the perspective of a person. So this person is leaving Chicago, and the first thing it tells us is we have 3 ways to get from one city to the next. Okay, so that tells me my first portion of my tree diagram should have 3 branches. So I'm going to have 1, 2, 3, just like that. Okay, and those 3 options are airplane, so I'll just put air. We have bus, or we have train. Okay, cool. Now it says once the tourists arrive, so once they finally get to Miami, it says there are 2 ways to get to the hotel. Either you take the hotel van or the taxi. So each of these branches is going to have 2 branches coming off of it. Because if you could take the train, you still got to get to the hotel. If you take the bus, you still got to get to the hotel. If you take the plane, you still got to get to the hotel. All right, cool. So those 2 ways to get to the hotel are either the van or the taxi. And from here on out, I'll just put V and T. So van, taxi, something like that. Okay, and it says, what is the probability that a person's trip to Miami costs more than 300? And you might be thinking at this point, now wait a minute, Coach Connor, there are no probabilities given in the problem. There are only, we only know how many branches we have. We don't know probabilities. You're right. However, we can still use our probability formula. So if we look at the top one more time, I can still use this. If I know the number of times an event occurs, I can divide it by the total number of outcomes, and I can still get a probability here. So I want to know the probability that my trip costs costs more than $300. So what I need to do is figure out not the probability of choosing each of these branches, but how much does each of these branches cost, first of all. Okay, great. So I know if I go the airplane route, this is $350. And if I take the bus, if I look at the table, this is $150. And if I take the train, this is $225. Okay, so that's first thing. Okay, the next thing I know, once I'm in Miami, now I got to get to the hotel. I know the hotel van is $60. So all of these branches here are going to be 60. Okay. And then I know the taxi. Let's see, give me another color. Give me blue. Okay, I know the taxi is going to be $40. So all of these branches are going to be 40. Okay, so let's think about this for a sec. What I can now do is I can go through each possible outcome of my journey. So there are 6 different ways to eventually get all the way to the hotel in Miami. And I can figure out what the total cost of that trip cost me. So right here, I have airplane and then van. That's going to be $350 plus another $60, right? So this is $410. Cool. Same thing here. Airplane then taxi. 350 plus 40, that's $390. Okay, then we have bus plus van, 150 plus 60, that's $210. We have bus plus taxi, that's 150 plus 40, we have $190. Then we have train plus van, that's 225 plus 60, this is $285. And then finally, this last possible trip I could take is $225 for the train plus another $40 for the taxi. That's $265. And I want to know how many of those events cost me more than $300. Okay, so I can do that real quick. This one cost me more than 300. This one cost me more than 300. And then a quick scan, I think none of those cost me more than 300. So in other words, the probability that my trip is greater than $300, okay, is going to be equal to I have 2 trips out of a total of 6 possible trips that I could have taken. This reduces to 1/3. And of course, we know that this is about 0.33 repeating or 33%. So we have a 1/3 or about a 33% chance that taking this trip is going to cost me more than $300. Okay, that is it for Unit 1, Lesson 1. Good job, everyone.